Floer cohomology is, and some work in progress. So it starts with the following observation that Paul Seidel made almost 20 years ago, which is the following. So if I take an isolated hypersurface singularity, and I look at Floer cohomology of the monogamy, which I'll explain later. I'll remind you what that is later, but it's some Floer cohomology group, sequence of Floer cohomology groups associated to that singularity, then it bears has some similarity with a certain algebraic variety called the arc space, or it's called the contact locus or something. Okay, so I want to explain just morally what the arc space is first before I talk about details. So very roughly, the arc space of say a singularity or of say a variety even, it's a space of holomorphic maps from the unit disk to that variety, maybe passing through this singularity if you have say a singularity you wish to choose. Okay, so it's just some space of holomorphic disks. Most people in algebraic geometry consider just formal disks, which are just the Taylor series. But for us, I think we actually, really it's the space of holomorphic disks for us. But in this talk, it's not so important. Yeah, so that's cool. So actually, I'm interested in something called, they call it the short arc space. Okay, as I said, so I'm only going to be interested in jets of such maps, but really you should keep in mind the short arc space a little bit, because I think that's sort of the key object. Yeah, so as I said, my personal opinion is the entire arc space is important if one wishes to study more complicated Floer theoretic objects. Okay, so what's the general goal? So my general goal is just to understand the relationship between Floer theory and arc spaces better. And I'm going to do it in the example that Paul Seidel mentioned in 2001, which is hypersurface singularities and the example of hypersurface singularities. But I'll explain some more general things at the end, although I guess I don't think I'll have enough time to explain it maybe, but we can always discuss some things afterwards. Yeah, so one hope is that it should make it easier to compute some Floer groups, a little bit easier, maybe not as easy as I would hope, but a little bit easier. Oh yeah, this is about work in progress. It's about some work that I promised people I would finish by last year, and it's not going to take. It's still got quite a while to go, but I think this is a worthwhile idea sharing, so I'm sharing it now. Oh yeah, I don't know if there are any algebraic geometers in this seminar, but I have an advertising spiel for algebraic geometers too, which is that you can prove results in symplectic geometry without doing much symplectic geometry. So, so that's another sort of advertising thing for this arc spaces and Floer theory. Okay, so let me just remind you or introduce you to some of the sort of key objects that I'll be talking about today. So the first is, I'm going to start with a polynomial, and it has an isolated singularity at 0, and it maps 0 to 0. So, And now I'm going to take a small sphere around the origin, and it's going to have radius epsilon. Whenever I state facts involving this sphere, epsilon is always sort of sufficiently small until the fact is true. And then I have the Milnor map, and this is the following fibration. So I just take the argument of F and I map it to the circle. And this is a fibration away from the F inverse of 0. And it's a symplectic fibration. There's a symplectic structure on the fibers. You just take the standard symplectic structure on CN, you restrict it to the fibers. So then you have a fibration and a sort of smooth fat, you know, a closed two form whose restriction to the fibers is symplectic. And there's a, you know, parallel transport maps. The kernel of this two form gives you a line field, and that gives you a connection on this fibration, and you can look at the monogamy map. Okay. So yeah, so the Milnor fiber of this fibration is a fiber of this map. Sometimes I might just take the closure of this fiber, so it may or may not have boundary. And then I have the Milnor monogamy map. So this is the, as I said, this is the monogamy. There's a natural connection given by the kernel of the standard symplectic form when you restrict it to the sphere, and that gives you a connection, and you can parallel transport sort of positively around the circle, and you get a monogamy map from the Milnor fiber to itself. Okay, yeah, so then I have a fact, which is that the closure of this Milnor fiber in S epsilon is a Liouville domain. And this monogamy map, which I'm always going to call phi sub F, extends to some sort of exact symplectomorphism of this Liouville domain. You might have, I presume you could have to perturb this fibration very slightly to make things work. So that's what I will do. Oh yeah, just remind you what a Liouville domain is. I know this is a talk for symplectic geometers, but so Liouville domain is an exact symplectic manifold. So it's a compact manifold with boundary, and a one form theta, so that d theta is symplectic. And if I look at the dual of that one form theta with respect to that symplectic form, it points outwards along the boundary of M. So that's a convexity condition. It's sort of technical, important, but sort of a technical condition. Okay, so far, what have we done? We have an isolated hypersurface singularity, and to that we've associated a Liouville domain and an exact symplectomorphism of that Liouville domain. And from that data, you know, we want to study the singularity using this data. Okay. Yes, I also want to talk about the contact structure. So this sphere S epsilon, so this tiny radius epsilon sphere inside complex affine space has a natural complex contact structure. You just take the sort of complex invariant part of the tangent space of the sphere, and then there's a fact, which is that if I look at F inverse of 0 intersected with the sphere, sorry, I should have put F inverse of 0 intersect S epsilon, then it's a contact submanifold of S epsilon. And this is the link of, this is called the link of F. Oh, I should say one thing. Actually, I should go back a slide. So I should say one more thing. For my purposes, I'm not really interested in the link itself. I'm rather interested in the link as a submanifold of the sphere. So as a contact submanifold of the sphere. You know, just like if you have a, you know, it's just, yeah. So I'm not interested in the link itself. The link has a contact submanifold. Okay, and then this is my favorite example. This is sort of, it's just x squared plus y cubed. So I have a map from C2 to C. It's given by x squared plus y cubed. The link is a trefoil knot inside S3. The Milner fiber is a torus with one boundary component. And then I have a picture here just describing the monogamy map. So, yeah, so to understand this picture, you consider, you just take a smooth fiber of F and you project to the Y coordinate, and that gives you a double cover. That double cover has three branch points, sort of three critical points, and that corresponds to these three sort of crosses here. And then you can, if you think about it, this surface I've drawn is a genus 1 with one boundary component, and the boundary component is a torus knot. And then the monogamy map, so there's a natural Z2 action given by sort of swapping the top and the bottom of this surface. And there's also a Z3 action rotating, there's a Z3 symmetry rotating this surface. And you know, those symmetries correspond to, if I look at the variable x here, if I send x to minus x, it preserves f. And also if I send y to a cube root of 3 multiplied by y, then it preserves f as well. And that corresponds to these two symmetry groups. And so Z2 cross Z3 is a Z over 6 action, and the monogamy map is the generator of this action. Well, it's not quite, because if I raise the monogamy map to the power of 6, it's not quite the identity. There's actually a Dane twist around the boundary. So what you do is you apply this Z3 rotation, then you apply the Z2 generator, and then the boundary has rotated by about a sixth. And then you untwist the boundary back to the identity. And that's what the monogamy map is. Okay, are there any questions? Okay. Okay, let me just remind you what Floer Cohomology of a symplectomorphism is. Again, I expect many of you are familiar with this, but I'm going to remind you anyway. So suppose I have any exact symplectomorphism of a Liouville domain. The only example I'm considering is this monogamy map. Then very roughly, Floer Cohomology is defined as follows. The generators are fixed points of this symplectomorphism. So you know, you have to perturb it generically so so that it's non-degenerate, and there's only finitely many fixed points. And also you have to worry about how the symplectomorphism behaves near the boundary. I'm not going to worry about that. It's a sort of very small sort of positive rate flow near the boundary, but we're not going to worry about this technical detail here. Another way I like to think about the generators of Floer Cohomology is as sections of the mapping torus. So the mapping, I have the mapping torus, which is just an interval cross M, and then I identify the ends of the interval using the symplectomorphism phi. And then, well, that's a natural fibration over S1, and I'm looking at sections which are constant, which means if I look at the image of this section, it's equal to some constant number here, some constant on M cross this interval. So the section is equal to interval cross, or another way of saying it is that, you know, there's a natural flat connection on 0, 1 cross M, and you look at the covariantly constant sections. And there's a correspondence between those sections and fixed points. Oh yeah, and then I'm not going to say much about the differential, but it basically counts holomorphic sections of mapping torus cross R. And that's the way I like to think about it. There's another way of thinking about the differential as some count of sort of strips on M, but I prefer to think of it as holomorphic sections of R cross T phi, the mapping torus. Okay. Yeah, so my grading convention is minus the Conley-Zender index, induced by the trivialization coming from Cn. It's I made that decision because I think that's what other people have done in the past, and I don't want to sort of rock the boat. I suspect a better grading for what I'm doing is really some sort of SFT index, but I'm not going to worry about that here. So some of my theorems have kind of horrible grading shifts in them, and that's because I'm choosing I'm not choosing SFT index, and I should, but oh well. Okay. Okay, and then I have a theorem, which is, suppose I have another complex hypersurface singularity. So suppose I have another, suppose I have another polynomial with an isolated singularity at 0, just as above, so another polynomial just like f. And suppose I have the monodromy map phi check f. Okay, so I have two polynomials, f and check f, and I have these two Milnor monodromy maps, phi f and phi check f. And suppose that there's a contactomorphism of the sphere S epsilon, sending the link of f to the link of check f. So in other words, suppose that the links of these two polynomials are identical as contact submanifolds of the sphere. Then the claim is that these Floer groups, the Floer cohomology of all powers of phi f and all powers of phi check f are identical. Okay. So these Floer groups are invariants of the link of f, viewed as a contact submanifold. Okay. Yeah. Oh, Paolo Gugini has raised a hand.
Yeah, is it the theorem is really about singularities, or there's any chance that it still holds if you take any open book supporting the standard contact structure of S to n minus 1?
Good question. Yeah, this theorem works for any open book, I think. I think I proved that. I think I'm beginning to forget what I've proved and not proved, but I think that's true. Yes, I think I proved it. It's on. I have a paper on something called log canonical threshold and something or other, and it's in there.
Okay. And what about other contact structures, other contact manifold than the standard in the standard sphere?
I'm trying to remember. I'm really trying to remember what I did. Let me think. I think it works for any contact. Yeah, you can have any contact manifolds and any open book, I think. Yeah.
Thank you.
Yeah, my real answer is just read what I read in that paper, and that will be the right setting. But I'm pretty sure it's that general setting.
Yeah, I wish I had the time.
Okay. Okay, so now let's talk about arc spaces. But as I said, I'm not going to consider the entire arc space. I'm just going to consider jets. And so the spaces that algebraic geometers call these contact loci. So let's start with the unit disk in C, which will always be denoted by D. And then I can define the dth jet space. Okay, so I'm going to write that as jet dCn at 0. And this is the variety of d jets of holomorphic maps passing through 0. Okay. So what does that look like? So more concretely, you can think of it as the affine space of n tuples of degree d polynomials whose constant coefficient vanishes. Okay. You know, d-jets are locally described by degree d polynomials. And then even more concretely, it's this set. So it's the collection of polynomials u of t, and it's a polynomial whose coefficients are elements of Cn. And as you can see, there's no constant coefficient. It's divisible by t. Okay. So, so this is just an affine space. So as a variety, it's just some sort of affine space. So this can be defined more generally for any variety pretty much. And, people study that. But I'm just interested in jets of Cn today. Oh, I have a little sort of schematic picture. So like a little wiggly line, a space of wiggly lines described by polynomials. Okay. Okay, what's the Deith contact locus? So I'm going to call that chi d of f. And it's the following subspace of that jet space that I described above. So it's the space of d-jets through the origin so that f maps this d-jet to the map t to the d in the jet space of the complex line. Okay. So again, I should probably describe this in terms of equations and stuff, and then I'll give an example as well so that we're absolutely clear what it looks like. Okay, so it's the subspace of d-jets that map via f to the d-jet of the map sending z to the d. Okay. Okay, so more concretely, it's described as the following thing. So I take the space of degree d polynomials whose coefficients are elements of Cn. And again, the constant coefficient is 0. And then I consider the polynomial f of u of t. I ask that it's equal to td mod td plus 1. So I look at all the coefficients of f of u of t, and then I only look at the first sort of up to the dth power, and I ignore all the higher powers of t. Okay. And then, so morally, you should think of it as the space of d-jets of holomorphic maps from the disk to Cn. Sorry, this should be here should be Cn here. And whose boundary sort of wraps around the singularity n times. Okay? So that's what you should think of these arcs. They're sort of spaces of things passing through the singularity whose boundary sort of spins around the singularity d times. Okay, so let's do an example, and we'll do my favorite example, which is x squared plus y cubed. So again, this is just the definition of so I'm going to look at the second contact locus, chi2 of f. So that's the space of two jets, so that when I apply f, compose f with this two jets, I get t squared modulo t cubed. So in equations, it's this. So a general two-jet in C2 looks like this. It's a polynomial whose coefficients are vectors, and there's no constant coefficient. And then I take this polynomial and I apply f to it. So f, I think of this as I apply f of the top and f of the bottom, and then I apply f of the polynomial, and I get the top squared plus the bottom cubed. And then I just solve this equation. I find all these coefficients, A21, A11, A22, A12, that satisfy this equation. So it becomes this, the only, this has got to be equal to t squared mod t cubed. Most of these powers of t are really high. The only power of t squared that matters is this one here. So the only constraint is on this coefficient A11 here. Okay. And then I'm really only interested in this as a topological space. So, as a space, it's just 2 copies of C cubed. Okay. Any questions? Okay.
Oh, sorry, Mark.
Yeah.
Are the jet spaces more complicated for more complicated singularities, or is it typically just gonna?
Yeah, they get very, very complicated very, very quickly, and they also can be quite singular. So this is a little bit misleading because this is smooth, but they can also be singular spaces as well.
Okay, cool. Thanks.
And now there's a conjecture by these people here. It's a bit funny because I was working on this paper before they made this conjecture, but oh well, they're the first one to publicly state it. So, and it's the following conjecture. So I take the Milnor monogamy map of F, I raise it to the power of D, and I take Floer cohomology. And the claim is it's isomorphic to compactly supported cohomology of this variety. And again, with this sort of ugly shift, which I think disappears if you use SFT index. Okay, so in their paper, these sequence of letters here are the same authors. This is the same paper. They have the following theorem, which is, suppose I write my polynomial as a sum of homogeneous polynomials, fm plus fm plus 1, etc. And the degrees of these homogeneous components go up. So the lowest degree component is fm. Okay. So then I could look at Floer cohomology of, oh dear, I ruined this. Oh dear. Okay. I don't mean the group, so this is not true. How do I say, let's fix this. Okay, so what I mean is when D is equal to M, this conjecture is true. That's what I mean, okay? And when D is equal to M, okay, so I corrected it. So when D is equal to M, these groups are isomorphic to compactly supported cohomology of the Milnor fiber of the first homogeneous component, Fm, okay? And so as a corollary, they get that the compactly supported cohomology of the Milnor fiber of the first homogeneous component, the homogeneous piece of the polynomial, is a contact invariant of the link. Again, of the link as a submanifold of the Fs epsilon. So this is actually an example. These people are algebraic geometers. They didn't write down a single contact form or symplectic form anywhere in their paper, yet they proved this symplectic result. Okay. Okay, so now my main theorem is that this conjecture is true in general, and I want to explain why it's true. So there's a reason why this is true, and I hope it becomes clear by the end of the talk. Does anyone have any questions about this?
Do you actually understand all the algebraic geometry?
I don't know. I'm not sure what to say about that. I know some algebraic geometry.
So you're going to write a proof for us symplectic people to follow is the upshot.
I'm trying my best to make it at a level that's sort of understandable to people who are not used to thinking about algebraic geometry. Denny O'Rourke raised a hand. So. I can't hear anybody. There's someone in the chat saying something too. Maybe I'll see. Could one prove an equivariant version of this? Discrete loop rotation on Floer side and multiplying by units of the jet ski side. My answer to that is, I think so. If one works very hard, it might be true. Yes, but I haven't thought deeply about this. But what I want to advertise is a proof technique which I hope works in lots of contexts. Is Denny O'Rourke? Oh, Denny O'Rourke's put his hand up. Can you state again why the left-hand side of the conjecture is the same as compactly supported cohomology of f at equals m? Oh, I should have. I read their paper and I've forgotten why this is true. But I can tell you what the key point is. So I produced a spectral sequence that computed these Floer groups, and they produced us. So I wrote a paper a few years ago that gave a spectral sequence computing this left-hand side. And they produced the same spectrum. I conjectured that there was the same spectral sequence for these groups, and they proved it. And so these two spectral sequences are identical. And somehow they just look at this spectral sequence that I used, and they somehow show that it maybe degenerates or something in this case. So it's the same. D is equal to M, and so they recover this compactly supported cohomology of FM. So they just play around with these spectral sequences that have existed before. I'll talk about these spectral sequences later on if I have time.
So you're saying there's not a direct, obvious geometric reason why for D equals M this is the same as just the usual cohomology of a Milnor fiber?
I'd have to look at their paper again to see exactly what's going on. I didn't think enough, but all I know is they looked at this spectral sequence. That's all I can say. I mean, I probably, they're looking at something like, you take a weighted homogeneous blow up of the singularity and look at that sort of structure somehow. Okay, let's just look at the conjecture in our example. So my favorite example.
Mark, you have another question?
Oh, somebody, yeah. Okay, let's look at the chat. The right-hand side carries a mixed Hodge structure. Does it make sense on the left-hand side? So I have no idea. I don't know. It was very interesting, but I don't know what to say. You're right, but I have no idea. It's a good question. Okay, so we're going to look at the case when D equals 2. We already computed the second contact locus, where it's two copies of C cubed, and you can just compute compactly supported cohomology. It's Z plus Z in degree 6 and 0 otherwise. And I had an explicit description of the monogamy map, and I can compute what the fixed points are. So, the phi, I'm looking at phi, the Milnor map, phi f, and I'm looking at phi f squared. So phi f squared is just this z over 3z rotation. And, well, you can just see there's just two fixed points. they must be of the same index. It's index -3 with my conventions, and so the conjecture is true. At least it's clear that the ranks are the same from this picture, I hope. Okay. Yeah, so that should be star is -3. That's a mistake. Okay. Yeah, so hence the conjecture is true in this example. Okay. Okay, so now I'm just going to spend
Stony has a
next.
Stony wrote something in the chat, Mark.
Oh, okay. Let's have a look.
Oh, never mind. Never mind.
Okay. Okay, good. I hope my example was right. Okay. Okay, so now I just want to explain the idea of the proof. I think that my slides are a bit long for this talk, so they will be online at some point so you can read the rest. But I'll try and give you an idea of the proof. And the idea is not, the key idea I hope is sort of, the sort of intuitive idea should be, I hope, fairly clear by the end, I hope. So, so what I'm going to do is construct a kind of PSS map from one space to the other space. Okay, and it's going to be like a jet kind of PSS map. So I'm going to call this EV, evaluation. Okay, so on a chain level, what is a PSS map? It's a count of holomorphic disks, and at the end, at the center of the disk, you have a sort of evaluation point, and you just take the jet at 0. Okay, so the boundary of these disks limit to some orbit on the mapping torus, and the center of the disk is at the singularity, and you just take its jet, d-jet. Okay, and if I look at the moduli space of these disks, there's this sort of, it sweeps out a cycle of d-jets, and so I get a map on the chain level. Okay, so I'll explain this in more detail with some pictures in a minute. Yeah, so this map is very similar in spirit to a map called the log PSS map defined by Ganatra and Pomigliano. I told you that the space that I think is really important for us really is called the short arc space, which is the space of holomorphic disks. And so I don't know, a useful, a kind of fun thing to think about, which I haven't really thought about myself carefully enough, is, there's a sort of PSS map to this space. Let's say you look at like Hamiltonian Floer homology or something, and you look at the usual PSS moduli space. And instead of just evaluating at a point, you just take this PSS disk and you just chop off the end, and you get a little disk. So you get some sort of cycle in the space of disks. And, you could ask things like, what does the Pants product look like? You get sort of these fun kind of like string topology-like operations with these disks. Anyway, that's just a side comment for people who might be interested in that. Okay, so let me just go in much more detail to for what I said. So, so the first thing is I don't really want to work with the Milnor fibration itself. I want to work with the sort of other description of the Milnor fibration, which is the following thing. So I look at the pre-image of a tiny disk, and I intersect it with a slightly less tiny ball, and that gives me some fibration, and it's basically the same as the Milnor fibration with a sort of singular point at 0. Okay. So this is the picture. So I'm interested in this region here. So the blue region intersected with the purple region or the pink region here. Okay, and so this gives you some sort of fibration with an isolated singular point at 0. Okay, so if I look at the pre-image of the boundary of this disk, d epsilon, then basically up to sort of isotopy, that's the same as the mapping torus. And that's the sort of object I'm interested in. Okay, so here I have my disk d epsilon. I look at the boundary, which is these 2 points that I've just thickened up. I look at the pre-image, and I get these 2 lines. Again, these 2 lines were really inside this ball, and that's my mapping torus. Okay, and now onto this sort of singular fibration I've constructed, I need to glue a cylindrical end, which is interval cross-mapping torus. And this gives me some large space, which I'm going to call E tilde F. So, and I also extend F over this cylindrical end in some nice way. You know, so it looks like the natural map to interval cross S1. So I'm not going to go through all the details of this because it will take ages, but here's the picture. So I have this region inside here. That's my original fibration, and it maps to this disk, which is this little pink piece here. And then I've extended it to a fibration over C by attaching this cylindrical end, which I've schematically drawn with these blue lines. Okay. Is anyone confused by what I've done, or have any other questions? Okay. Okay, so now let me describe this PSS map. So I want to describe it at the chain level. Okay. So I want to compute this chain. I want to compute what is this map at a fixed point of my symplectomorphism. And again, I'm not really interested in fixed points. I'm interested in section. You know, as I said, there's a sort of correspondence between fixed points and flat sections of my torus. So the first thing I do is I look at the corresponding flat section. So I choose the unique constant d-fold. So remember, I'm also considering phi to the d, but the mapping torus I'm working in is just the mapping torus of phi f. So I choose the unique constant d-fold multi-section of my mapping torus passing through P. So what does that mean? Just to be clear, what does that mean? So this is the unique map gamma from the circle to my mapping torus, whose image is constant. That's what it means. The image is constant and passing through P. And so that its composition with the natural map to S1 is the d-fold covering map, which is just a map, you know, wrapping the circle around d times like this. Okay. So, okay, so that's the orbit I'm interested in, and I want to know what is the PSS map doing with this orbit. So now I need a moduli space, and I'm going to look at the moduli space of holomorphic maps from the complex plane to my space EF tilde. Sorry, I think I wrote E tilde F, and I really meant EF tilde. It doesn't matter. This is it's that picture I drew with these cylindrical ends, and it's satisfying the following properties. So the boundary of this holomorphic map limits to my orbit gamma. When I take F tilde and when I project this Floer trajectory to the base, then it's just given by the map Z goes to Z to the D. And you can already see that some of this jet space stuff is appearing. We've seen this equation before. And U of 0 is 0. So again, here's a schematic picture of what is going on. So this is my So this is my singular fibration with these cylindrical ends attached. These two orange lines represent my holomorphic multi-section. The holomorphic multi-section passes through the origin, And these pink dots, these represent my orbit, and this holomorphic multisection is limiting to this orbit corresponding to my fixed point. Okay, so I'm counting, this is my moduli space, basically. Now, there's some subtleties here that I want to explain in a minute. But for the moment, this is the picture you should have in your head and you should remember. Does anyone have any questions? Okay, great. Okay, so now we have a natural evaluation map. You know, we have our moduli space MP, and it evaluates to this contact locus, and it just sends my holomorph. You know, these are holomorphic maps from C, so you know you can just take the d jet at 0, and I get an evaluation map to my jet space. And you know, I suppose if everything works out, then it represents some sort of like locally finite homology cycle, and so it represents a sort of element in, you know, the chain complex of compactly supported cohomology modulo. Well, I say some details, but actually it's a lot of details. Okay, I'm going to just say some technical things about what issues might happen when you try and do this sort of naively. So the first problem is that this space is singular, which I don't want to really deal with singular spaces. In general, this is singular. The example I gave is smooth, but in general, it's singular. However, it's, you know, it's a subvariety of this jet space, which is non-singular. You know, this jet space is just affine space. And so, you know, what you can do is sort of consider some sort of larger cycle given by some slightly larger moduli space, and then just sort of intersect it with this variety, and you get some cycle in this variety. So that's not a problem. You know, writing this out is a little bit of a pain, but. And then my claim is standard sort of PSS style gluing and compactness arguments ensure this is a chain map. Okay. So now we have this evaluation map. We have a map from one of these groups to the other one, a map from the Floer group to this algebraic group. And now I want this algebraic compactly supported cohomology group of this algebraic variety. And now I need to show it's an isomorphism. And again, there's some details that you don't have to really remember, but I'll just say them just to be honest, which is technically I shouldn't really work with this jet space chi-d when I'm trying to prove this map is an isomorphism. I actually have to work with a higher jet space. So I don't work with d jets, I work with some L jets, where L is huge, some huge number. And I'm going to suppress that detail, but that's just a sort of, so this issue also appears in this paper by Brook and the other people I listed earlier, when they proved that this spectral, when they proved this result involving this sort of Milnor fiber of the first homogeneous sort of part of the polynomial. But I want to suppress that detail for the moment. Okay, so now what is the key idea of the proof? So I mean, I've told you the first key idea, which is use a PSS map. That's the first key idea. And now I want to know, what is the key idea proving that this PSS map is in fact an isomorphism of groups? How do I prove that it's an isomorphism? So the idea is as follows. So we construct filtrations. One's called F and one's called F prime. And the first filtration is on the chain complex underlying compactly supported cohomology of my contact locus. And the other filtration is some natural filtration on Floer cohomology. The filtration on Floer cohomology, there's sort of really only one main one that if you've done Floer theory, you know what that filtration is. It's sort of basically the action filtration. And then once we have these filtrations, we want to show that the PSS map respects these filtrations and induces an isomorphism of the associated graded filtration. And these filtrations have both appeared before, and they come from spectral sequences computing both of these groups. So the spectral sequence computing this group was constructed by Brook, so the same authors that I mentioned earlier. And then I constructed a spectral sequence computing this Floer group a few years ago. And so these are the natural filtrations that they've already appeared before. Okay, so what are these filtrations? So both filtrations are constructed using a resolution. Now, technically, to make life easier, usually the resolution is a very special kind of resolution, which I called a multiplicity D-separating resolution. But again, I'm not going to mention that detail here because that's not important. Okay, so I'm just going to remind you what a resolution is. So by Hironaka resolution of singularities theorem, I can sort of take my singularity and sort of blow up at a bunch of points. And as a result, I get some holomorphic map from some complex manifold Y to Cn, so that B is an isomorphism away from the origin. And then if I take the pre-image of the singular fiber, or the central singular fiber of my polynomial, then it's a union of transversely intersecting complex hypersurfaces, which I'm going to call E0 to EL. And there's some nice integral Kähler form. When I say integral Kähler form, I mean a Kähler form that lifts to an integral class. And so it's a Kähler form coming from some nice line bundle somewhere. And the Kähler form has this property that it's sort of exact away from the sort of blow-up locus where I've done all these blow-ups. All these blow-ups are done over the origin because B is an isomorphism away from the origin. Here's a schematic picture of this resolution that you should keep in mind. Here's my singular fiber, F inverse of 0. Here's my blow-up map, blow-down map. E0 is going to be what we call the proper transform of F inverse of 0. So you take the pre-image of F inverse of 0 minus 0 and take its closure in B. You get this E0 here. And then you have other exceptional, what we call exceptional divisors, so other complex hypersurfaces, E1 and E2. Y is my space here. Okay. Okay, so what is the filtration? So this is going to be, the filtration on compactly supported cohomology is going to be induced by a function on this space, chi d of F. And what is this function? I'm going to assume D is large, but it doesn't matter. This is just sketchy, so it doesn't really matter. So what I do is I take a holomorphic map representing any element eta of my jet space, chi d of F. So the D jet of U is representing an element of this space. And then I define F of eta to be this limit. What is this limit? So, this jet is represented by a little holomorphic disk in Cn. And then by the removable singularity theorem, I can lift it up to the resolution Y. And then I can take theta, which is the one form, and integrate theta over the boundary of this disk, and then take some limit as the disk gets smaller and smaller. This really only makes sense if D is very large. Otherwise, it doesn't really make sense. Okay, so in your mind, you should think just little disks, and you're integrating theta over the boundary of this disk. That's what you should think of in your mind. Okay, And this induces a filtration, and this is basically what these other authors proved, so Berdeur and et al. Okay. So yeah, as I said, the key point here is by the removable singularity, this map U admits a lift to Y. Sorry, this should be Y here, and this lift intersects some stratum in the union of the exceptional sort of these hypersurfaces E0, E1, etc. And the value of F is determined by this stratum. And so this filtration has a sort of, the values are determined by the strata of the blow up, the exceptional divisors, these complex hypersurfaces, EI. So here's the picture. Here's my little arc, U. It has some lift by the removable singularity to Y, and it intersects some stratum of this union of complex hypersurfaces. And the filtration is basically determined by that stratum. And it's a filtration because it's actually a filtration morally by Gromov compactness. So if I have a family of these lifts, U tilde T, what happens is it degenerates to some limit. And this limit is like a disk with some sort of bubble tree by Gromov compactness. And the point is, if I integrate the Kähler form over this bubble tree, it's positive because it's holomorphic bubble tree. And so the filtration sort of goes down when I take some limits. And so if I have a cycle that, you know, it sort of respects this filtration. Okay, yeah, so that's what I just said. Okay, I've got 4 minutes. Okay, so that's the first filtration. So the first filtration is just the integral of theta y. And now I want to describe the filtration on the chain complex underlying Floer cohomology. And that's basically the action filtration. So, the first thing you have to do, though, is choose the right contact form. And the contact form is as follows. You take the mapping torus and you sort of put it really close to the union of these hypersurfaces, union IEI. So here's the picture. Here's my singularity. I move my mapping torus, which is these two pink lines, very close to the singularity, and then it kind of hugs these exceptional divisors. And then the point is the sort of Rabe dynamics is very nice. The Rabe orbits correspond to strata of these complex hypersurfaces. Okay. And again, the filtration is basically given by integrating theta y over each orbit. Okay, so both filtrations are given by the integration of theta y over some circle, and that's the point. Oh yeah, so again, these orbits come in families corresponding to the strata, and the key point is the strata are sort of, the families are very similar. You know, both the families coming from the contact locus and the families coming from these Rabe orbits are the same. And so the PSS map respects these filtrations essentially by Stokes' theorem, because, you know, we're just integrating theta y over some circle. And also, since this mapping torus is somehow close to these divisors, the sort of holomorphic multi-sections defining the PSS map have very small energy. And as a result, these filtrations corresponding to my orbit gamma, F prime of gamma and F of the evaluation of gamma are very, very close. And so, you know, I'm dealing with some moduli space of disks, and these disks have very, very low energy. And, you know, if you have a moduli space of things which have very, very low energy, then, you know, they're usually essentially determined by topology. And that's the point. Yeah, so as a result, the PSS map induces a quasi-isomorphism a quasi-isomorphism of the associated graded chain complexes coming from these filtrations. And these disks have very small diameter in the resolution. Okay, so here's my schematic picture of what's going on. See, the point is I have this very, very tiny disk here, and it basically looks exactly the same, sort of basically as the, as the corresponding element of the moduli space. And here it is over here. Okay. So time is up, but all I want to say is basically, so the key point is, the reason why this PSS map is an isomorphism is that I have some contact form on the mapping torus, and the orbits come in families corresponding to the strata of these the exceptional locus and these divisors EI, and also the filtration, the sort of elements of my jet space also correspond to various strata of these the same strata of this union of divisors, and using that sort of structure, you get your quasi-isomorphism. So I have more of my slides, but we'll put them online so you can read the rest later. Okay.
Right. Thank you very much, Mark. If there are any questions, it's a good moment to ask.
Are there like applications of having these kinds of relations between Floer cohomology and sort of like more traditional singularity invariance, or is it just kind of like a yay, Floer cohomology encodes a lot of the same?
Yeah, at the moment, I haven't really thought of some very good applications. One thing I thought would be interesting, I suppose, was it might be a nice way of computing certain, flow groups of certain families of singularities, like, say, Newton non-degenerate ones. But there are other techniques which are probably just as good for doing that.
At the beginning of your talk, you said that you had the hope that it would be easier to compute Floer groups. Is that because you'd be able to do it like purely in terms of non-Floer data for specific examples, and just look at like the information from the traditional singularity perspective?
Yeah, I mean, yeah. So, you should be able to compute things that you couldn't compute before. For instance, it gives you other spectral sequences. Like you could look at you could look at sort of smaller resolutions and look at spectral. You could look at, say, an orbifold resolution of your singularity or something, and look at and you'll have some natural spectral sequence over Q, and so you can compute these groups over Q quite easily without needing to work so hard. I haven't, I decided that the main point of this paper was really just going to be about jet spaces and Floer theory, and I feel like there must be something useful there, but I haven't really thought too deeply about a sort of real application yet. I was at Kyla Siegel. You mentioned that there should be generations refinements which require non-formal version of the arc space. Could you say a word about that? Yes. Okay. This is highly speculative stuff. But let's say, the reason why I became interested in arc spaces was because I was studying general isolated singularities of varieties. So not just hypersurface singularities, but you might have some singularity, which is, you know, not even a complete intersection or something, and you want to study, say, the relationship between the link of that singularity and the sort of algebraic geometric properties. And so, you know, one of these properties I recovered was called the minimal discrepancy. And then I noticed that this, you know, some of these things have relationships with arc spaces that algebraic geometers were interested in. And so, you know, an interesting question would be, if I looked at a contact invariant of a general isolated singularity, you know, not necessarily, if I take a general isolated singularity of a variety, and I look at just the link, you know, so there's no Milnor fibration, I just look at the link, and I look at some sort of contact invariant, like contact homology or something, or, and I ask, can I compute contact homology? And my claim is that, you know, this should be some sort of space of some sort of cohomology of some sort of space of holomorphic disks passing through the singularity, but it's not quite as simple as just taking cohomology or something like that. You have to build some sort of, because like contact homology could be infinitely generated in every single degree, and there are examples like that happening. And but you know, I was hoping what would happen is you could build some sort of, say, spectrum or something from this arc space of holomorphic disks passing through the singularity, and you know, maybe you could compute, say, some sort of contact homology group of the link from it. This is very highly speculative. I have no idea if this is true. The reason why you need disks and not just, say, formal jets or something is that, you know, that there are sort of computations by people like Kolar saying that, you know, these spaces are fundamentally different in certain examples. And, you know, as I said before, you know, I had this filtration. Oh, I won't go back. There's this filtration where, you know, you have to integrate over the boundary of a disk. And so you need an actual disk and a boundary of the disk to integrate sort of theta over to get your sort of filtration and prove that it's an isomorphism. So what I'm saying is highly speculative, but I think it's worthy of maybe thinking about at least. There's some other generalizations. I could go to the end of my slides about spectral sequences computing symplectic cohomology and things like that as well, but maybe I'll leave that to people to read on my slides later on. Ah, yes. Yeah, so I think there should be some way of describing the product structure. You know, there's actually a whole multitude of operations on these flow groups, and it would be interesting to know what they correspond to in this jet space. And, you know, you have a PSS map and you have all these gluing and compactness theorems, so it must correspond to something. I mean, you know, I always imagine, you know, you have these holomorphic disks, they're sort of moving about, and, you know, every so often their boundaries touch and you can sort of glue them, and it's like string topology or something like that. So you know, maybe this product corresponds to something like this. But I haven't thought about it carefully enough, and it's something that I would like to investigate further, definitely. Okay, Igor Shalukin. Could you use some calculations on the arc space side to say new things about MCG mapping class group? I don't know. Yeah, I don't know. Yeah, I haven't thought about it. Yeah, you know, maybe, I'm sure there's something. I mean, yeah, I haven't, to be honest, I haven't thought about some really like dramatic applications yet that I could use. But you know, every so often, you know, one of the reasons why one of the every so often I get emails from algebraic geometers asking, is this an invariant? Is this a contact invariant of the link? Is that a contact invariant of the link? And this is my sort of gift back to them, saying, no, just look at this. And but I haven't thought about things like symplectic mapping class groups. I'm sure there must be some interesting things to say. These arc space, having said that, cohomology of arc spaces isn't compactly supported. Cohomology of these arc spaces isn't like the easiest thing in the world to compute, but I think it's easier than Floer theory, definitely.
Okay, so let's see if there are other questions. I think we're basically at the end of our questions. So I don't see anything on chat more.
May I ask a question?
Yeah.
So this pink stuff on this picture, so do I understand correctly that they're just contactomorphic?
Yes.
That this
yes.
is the same object?
Yes, yes.
And your resolution of singularities was needed for defining the second filtration?
Yes, yeah. To define the filtration on the arc space, you need the resolution to do that.
So you cannot do this just directly on this right part of.
No, I can't. There may be a way of doing it, but I don't know how to do it. But I have this feeling. Yeah, at the moment, the only way I know how to do it is choosing a resolution and constructing filtration from this carefully constructing my contact form using this resolution and carefully, and then comparing it with the filtration on the arc space. And I don't know how to. This is the only way I know how to put filtrations on the arc space using a resolution.
And a kind of very stupid question. So you have several hypersurfaces. So formally speaking, each of them defines you some kind of filtration, right? Separately, I mean.
When you say several hypersurfaces, what do you mean?
So just on this picture, there is a 1, a 2, and so on. Yeah, so can look at intersections with the.
Yeah. So there's all these complex hypersurfaces.
Yes. So you will just take one of them. And
yes.
Can I define filtration in this way and then the second?
So each hypersurface has a kind of I think to define a filtration you need all the hypersurfaces together, because together with this scalar form omega y, which is basically a choice of some sort of ample divisor in algebraic geometry. Mm-hmm. And you need all that data together really to define this filtration. And the hypersurface, I could change my ample divisor without can I do that? No, I can change my ample divisor without changing the hypersurface, and it will give me a completely different filtration. And so you need all the data together to define this filtration.
Okay.
Does the map F that appears in the definition of the filtration as a natural description in algebraic geometry some multiplicity intersection number with?
Yeah, it does. So there's some ample divisor. It's some sort of intersection. It's some sort of you have these little like jets, and you have this ample divisor. And then you can pull back this ample divisor. The ample divisor can be pulled back to that jet, and then you have the order of the ample divisor along the jet, and that's sort of basically your filtration value. So yeah, it has a purely algebraic description. Oh, okay, 1 second. Is there a way to use this to define motive integration in symplectic geometry? That's hard to say. I feel like, yeah, motive integration is usually a lot sort of stronger somehow than symplectic geometry. So somehow it's quite algebraic, and I'm only, you know, somehow the only part of the motivic integral that I'm really sort of extracting really is the sort of Euler characteristic part of it, you know. So the other sort of parts of motivic integration are a bit, but they may not be recoverable in any way in symplectic geometry, but yeah, I don't know that having said that, there is something interesting which might be worth exploring. I don't know, which is there's this really nice paper I really like that I get a lot of my students to read sometimes, which is a paper by Otto van Kurt and Megay Kwon on the mean Euler characteristic of homogeneous singularities. Mm. And they compute it for sort of just the sort of the sort of diagonal weighted homogeneous singularities, but there's loads of other ones, and I suppose you can just use their calculations to compute it for other ones as well. But you know, there's a sort of kind of motivic kind of property of these mean Euler characteristics, in the sense that they have a sort of additive property. You know, if you sort of take a weighted blow up at the origin and resolve one of these, sort of partially resolve one of these singularities, and sort of the sort of mean Euler characteristic is kind of local on that weighted blow up. But I don't know what to do with that. But it's sort of anyway. What's next? Is there a way to phrase your results purely in terms of the cohomology of the resolving devices EI instead of the cohomology of arc spaces? Possibly, yes, but it's an extremely complicated story. So there's this ongoing work by Mark Gross and Dan Parmigiano, which their results, they take a affine variety and they compactify it using a smooth normal crossing divisor, and then they say we can compute. You know, their goal is to compute. They believe, and their goal is to compute symplectic cohomology of the affine variety completely using relative Gromov-Witten invariance. And now there should be a similar description here. You take a resolution, and then you build some sort of chain complex using the sort of strata of your resolution, and there's some sort of differential, and it's some sort of relative style Gromov-Witten invariant. And so there might be some way of understanding these groups upstairs using these ideas, but my understanding is it's a very, very complicated story, and so I can't say more than that.
All right, so maybe it's time to thank you again, Mark, for a very interesting talk. So, thank you very much.